This session is on decision trees and random forest. So we'll be looking again at probabilities. So we're getting used to probabilities now. We looked at them in logistic regression and conditional probabilities in naive Bayes. And we're going to discuss how probabilities and the theory of information are related. So this is our tool for how we construct decision trees and forests. And let's just see what those look like. So let me just make this full screen. There we go. You probably would have all seen a decision tree before. Unfortunately, you get a lot of decision trees in, silly horoscope articles and things like this. If your mood is this, then you're an Aries or something like that. So we're not interested in those. Decision trees can actually be very useful, and they are very good machine learning technique. So we'll take this example here. We're interested in predicting if someone, based on a series of questions we ask of them, are likely to develop stroke or that they won't develop stroke. So we can predict if they're going to develop stroke in the future. And as humans, we would, even if you don't have a medical degree, you're not a clinician, we'd have a pretty good idea of what kind of questions to ask. So the first question we have is hypertension, i.e. is your systolic blood pressure above 140? That might be a good question to start with. Do you have high blood pressure? Then we'll look at your age, physical activity. Do you have high cholesterol? All sorts of these questions, which we know as humans that we've learned are useful. And the way the decision tree works is you just either answer one way, yes or no, and you just end up following it down, depending on which questions you answer and how you answer them. You'll end up in one of these gray boxes. So these are called the leaf nodes of a tree. And this is where the boundary decision is made on whether you're likely to be remain healthy or if you're likely to have a stroke. And let's just see how this works, because it's not quite as simple as yes, no, healthy or stroke. Let's visualize some data points and how these people answer various questions and where they end up. And we can see how we can arrive at these decision boundaries. So this is what the feature space will look like. On the left, we are starting off our decision tree. So we're going to have one question, and the first one is feature 1 greater than some threshold C1? And on the right-hand side, we're going to plot F1 against F2. So we can take this question and we can assign an area within this graph or a partition in this graph based on this question. So again, the question was, is F1 greater than some threshold C1? And, F2. Yeah, so I made a correction there. So it should be F2. I did these in PDF and they're really difficult to fix. So, is some feature 2 greater than C1? So we've partitioned this off. We've got this partition on the right-hand side. Well, this area for F2 is greater than C1. Then this partition on the left for F2 is less than C1. So that's the first thing we do. We've gone on 2 routes, one on the left, one on the right. And you can clearly see that if this was yes, then this would be this partition. And if this was no, then this would be this partition. So we keep doing this. We're going to ask a question now. Is F1 less than some threshold C2? And remember, this question only applies to one of these partitions. It doesn't apply to both. So however people answered this first question, we're now only going to ask this second question of people that were either in one or the other, whichever it may be. So we're going to say, is feature F1 less than some threshold C2? And remember, this is only going to affect one partition. So we've gone with this partition here. And this straight line does not extend into this partition over here, because this question is your F1 greater or less than C2 only applied to this partition over here. And we can keep building up the picture by asking more questions. So here we have another. And again, it will only affect people in this partition now. So anyone who value of F1 was greater than C2, i.e. just from here, so this top right on the graph, we're only asking this third question of people in this partition. And we just keep building up the graph like this. And eventually what you'll end up with is something like this. Now we can take, let's look at a few of these partitions. We have the one in the bottom right here. So if we just say, for example, all the red dots are people that went on to have a stroke, and all the blue dots are those that remained healthy. In the bottom right partition, clearly you can see whatever questions were asked of these people along the line, every single one of them ended up in a leaf node, you know, this one, this one, this one, whatever, where they all had stroke, which means that if another person, someone walks into the clinic and you're going to try and predict if they will have a stroke in 5 years or something like that, you ask them all the questions and they end up asking the exact same questions and give similar answers to all of these people, they will end up in this partition or leaf node. And you can say to them, based on our training data, the company that you've kept is that you will end up having a stroke, 100%. Everybody else that answered the questions the same way you did, they all ended up having a stroke within 5 years or something like that. This one's pretty clear cut. But then if we take this one here, this large partition, perhaps, you know, just eyeballing it, I would say maybe 3/4 of this leaf node remained healthy. So that means you could say, based on your training data, if a new person were to come in and answer various questions, if they ended up in this leaf node, because they answered in certain ways, you would say to them that you have a 25% risk of developing stroke. So that's how these class boundaries are laid out. You know, for one thing, like in logistic regression, you look at the binary case, yes, no, lung cancer, yes, no. Here you can have stroke, yes, no. But like in logistic regression, where you have an associated probability, we can clearly see that you have a probability based on the distribution of the two classes within each leaf node. So that's good. So random forest and decision trees, they work exactly the same. This is what's happening when you build a tree. The way they work is that you can get your hard class boundary, which is yes or no, or you can also get the class probability, which is good. The big question then is how did we know to ask these questions? Specifically, if you want to determine if someone's going to have a stroke, why do we ask things like, is your blood pressure above 140? Things like this. And so training a decision tree, it means that we would like to get our machine to understand which questions are relevant. And not only that, in which order as well. So you'll notice in the decision tree, we asked hypertension first. That's a question which is really handy to ask of every single person in the cohort. Some questions, for example, if you have elderly people, so you've asked a question, what's your age? And you have people that are 95 years old, it's pretty pointless asking them, well, how much exercise do you do? Are you on the treadmill? Okay, so we would like to ask relevant questions as further up the tree as possible. So i.e. we're asking the better questions in order. So yeah, if you wanted to get a machine to distinguish between which patients will have or go on to develop cardiovascular disease or not, you know, asking which football team they support is a useless question. Asking about blood pressure is a useful question, you know. However, if a machine only learned that blood pressure itself is useful, but then it asks something like, is your systolic blood pressure above 1? This is clearly not useful because unless you're dead or a zombie, your blood pressure is always going to be above 1. So there's lots of things that we need to optimize on, not just what feature or what column of data you're going to use, but what's the appropriate thresholds that you ask. And so it's quite easy to see that better questions will give us more information. You know, in this case here, where you ask, is the systolic blood pressure greater than 1? Well, every single person is just going to move into one leaf node and no one's going to move into the other leaf node. So that's a useless question. Well, so now we have to talk about how can we teach machines to find good questions, or i.e. As you see here, how can we teach machine learning algorithms to split data in an optimal way that helps us with classification. And so we can talk about how they do this in terms of information. And when we say, if you ask this question, question A, you gain more information than if you ask question B. So we need to try and understand how machine learning algorithms can measure information so that when they ask a question, they know if that was a good question or a bad question to ask. And so can we measure information? Yes, we can. So we're going to think of, I'm sure you've all heard of bits, 64-bit cartridges and so on, bits in our computer. But when I'm talking about a bit here, I'm talking about basically a binary state encoded by 1 or 0. So I think you'll all be familiar with a binary bit. So in a binary bit, we are assuming that there's a 50% probability of being either 1 or 0. And you only need to ask one question to split this data. So again, we're talking about how can we train algorithms to ask appropriate questions. Well, you only need one question to determine if a state is in 1 or 0. So in general, for two-state systems, and this is just 2 data points, if you like, you only need one bit of information. Okay, well, what about 4 states? How many bits or other questions are needed? Remember, we're talking getting algorithms to learn questions. How many questions are needed to know which state the system is in at any one given time? So we're going to play a little game just to illustrate this, and it's playing guess what number I'm thinking of. So this is our 4-state system. So just, while we're thinking about classes, lung cancer, yes or no, sure, that's a binary state, 0 or 1. What I'm talking about here, when we have 4 numbers, is actually we have 4 different classes. So this could be low risk, medium high risk, and high risk. And there'll be a certain proportion of people that have their label as 1. So the ground truth is 1, i.e. they are low risk at developing stroke. 2, a certain proportion of the people in our training data will have a label of 2, and so on. In either case, the class I'm thinking of, or the number I'm thinking of, is number 1. How many questions would you need to ask to determine which number I'm thinking of, or which class I'm thinking of? So, an easy first question we might think of, or an efficient question we can think of, is the number I'm thinking of less than 3? And this splits our data in half perfectly. And I either give you an answer of yes or no, and I'll just say yes. And you're back to your binary state problem again. So we just ask one more question, and you know which state I'm in. Okay, what about an 8-state system? So again, I'll just think of the number 1. Where would you start? I've probably given the game away a bit because there's a large gap here. You could just say, is the number you're thinking of less than 5? In which case, that's our first question. Now we're back to our 4-state system, so we need to ask another question. And we're back to our binary state problem, so we ask our third question. So we can think of how we can measure information based on a binary bit. That's a nice, easy example. And I wonder if any of you have spotted a pattern in the number of states we have and how many questions you need to ask. So does anyone know what this function is? So as we have 2 states at 4, we double the number of states. We have to add one more bit or one more question to determine what state we're in. So those of you may have thought about this. This is a logarithmic function, not logistic function, a logarithmic function. And here you can see, in our 2-state system, we have to ask one question. In our 4-state system, we have to ask 2 questions. In our 8-state system, we have to ask 3 questions. So in a 6-state system, we don't have to ask 2.68 questions. The way you can envisage this is if we had maybe 600 states, you would have to ask 268 questions. So try and think of it like that. So yeah, we have this nice function which describes how we think about bits of information. And you can see quite clearly how they correspond to the number of states, to the number of bits or information you have in your system. And so Claude Shannon, who is an American mathematician, he's known as the father of information theory, and we think of bits of information thanks to his theory of information. And so he was very clever because he found a way to relate probabilities to measuring information in a system. So yeah, he realized this relationship. And that is that the number of bits of information in a system is log 2 of the number of outcomes or states, if you like. Number of outcomes, number of states, they're the same thing. So 8-state system, there's 8 outcomes. And he realized that the number of bits in any one system is log to the base 2 of the number of outcomes or the number of states. And we can think of probability in this situation. So when we talked about logistic regression, we found a way to relate odds and probabilities. Here we can relate the number of outcomes or the number of states in a system as 1 over the probability. So this means that if probability of one outcome is P, then 1 over P is the total number of outcomes. And then the way logs work, if you take the minus log of something in the bracket, you just take the reciprocal. So that 1 over P, when you take the minus log, becomes minus log 2 of P. Just take the inverse. And this was his equation for this. So the number of bits equals minus log 2 of the probability. So that was Shannon's theory. That's how you measure information based on probability. We'll just go through a worked example. So if we have 3 bits of information, we can just use a sleight of hand just to rewrite this. So this 1 over 8, this means 1 over the probability. So if we have an 8-state system where there's equal outcomes of observing each state, i.e. the probability is 1 over 8. 1 over 1 over 8 is 1 over the probability. So we'll carry this through. So if you do 1 over 1 over 8, this becomes 8 over 1, which is the number of outcomes. And if you take minus log 2 of 8 over 1, you get minus log 2 of 1 over 8. So again, that's this log behavior coming in if you reverse the sign. And this equals 3. So clearly this holds. Shannon's theory was that the number of bits in a system, or either information in a system, can be measured via its probability of outcomes in the system. This means that for every time we randomly pick an outcome out of 8 possible outcomes, we receive 3 bits of information, i.e. the state on average will give us 3 bits of information whenever we observe an outcome. This is in a special situation, and we're using 8 outcomes, and there's equal probability of observing any one of those outcomes. Out of the 8 classes we have in our problem, they're represented equally in our training data. Whenever we look inside that system and we observe one data point, we are getting 3 bits of information every time on average. So this was Shannon's theory. And we'll talk about how he defined his measure of entropy. We just need to quickly point out that we were looking at the top, or where y is greater than 0. Well, we were interested in the number of outcomes and how many bits of information this gives you. Shannon's theory allowed us to look where y is less than 0. So we see here that the number of bits minus 3 is equal to 1 over 8, 0.125, but obviously you take the minus sign over. So his special thing was to look at this side of the curve rather than this side of the curve. That's the relationship we were looking at. So just to recap, if we have 8 classes of equal probability of being picked, each time one outcome is picked at random, we are receiving, on average, 3 bits of information. So every time we peek into the system, on average, we will expect 3 bits of information. And if we think about it like this, if we would like this equation to describe how much information we receive, if we pick 2 times or 4 times or 100 times, can we calculate the total number of bits in the system? So remember, we just pick once, just one, we look inside, but we'd like to say, if I pick maybe 100 times out of this equal state system, how many bits of information will I receive? So in our 8 outcome system, we sample n times and note how many bits when the number 1 appears. So remember, our 8-state system with the number 1, 2, 3, 4, 5, 6, 7, 8. And we note that when we get the number 1, this appears with a probability of 1 over 8. So on average, we would receive 1 over 8. So this is our equation before, minus log 2 over 1 over 8. But only when we get the number 1, when we have to multiply this by the probability of seeing 1 in the first place. So this equals 0.375 bits. So for any one particular outcome, if I was only interested in one outcome, when we're thinking about this 3 bits of information on average, I don't really care what outcome I'm getting. I just want to look once and get an outcome. On average, we receive 3 bits of information. If I'm now only interested in the number 1, I will, when I see it, I only receive 0.375 bits of information when I'm only interested in the number 1. So for just one of the outcomes, on average, we'll receive 0.375 bits because this is just 1 over 8, or we only see this number 1 over 8 times. But obviously, there are 7 other outcomes. So the total number of bits of the equal 8 outcome system or state holds is obviously 0.375 times 8, which rebuilds us back to our 3 bits. And this allows us to rewrite our equation in a certain way, which is the Shannon entropy. So this is the total information in a state, or the Shannon entropy, H, is equal to the sum of minus P probability multiplied by log 2 of P. So this is what we were talking about before. On average, to measure the information in a system, you don't really care about what outcome you're getting. You just have this, but you rebuild this, rewrite it in a certain way by including the fact that you only observe certain events, certain amounts of the time. So this is the Shannon entropy. And this equation tells us, given a state, what is the total information you will receive on average from this state? We've been looking at a nice, easy example, though, with equal probability. So let's look at a state with unequal probabilities. So this might be our class representation. Most of the data points in this class are in the blue class, and you have a minority that are in the red class. For any one given outcome, we can calculate just the information for just that outcome. So for blue, if we receive 1 blue ball, we get 0.41 bits of information. And if we get a red ball, we receive 2 bits of information just by plugging in these values. So why is there such a discrepancy between the bits of information you receive when you get a red ball to the bits of information you receive when you get a blue ball? So we know that the red, it's rarer to see a red ball. Does this translate into more information when we get a red ball? Well, I think it does. So if you think about it like this, just really simplistically, we know that the sun rises every day. This is a really non-rare occurrence. It happens all the time. So whenever we wake up and we see the sun the next day, do we really get any more information? No, we don't. We know it's going to come up each day. However, if you woke up in the morning and there was a solar eclipse, suddenly all the news outlets are reporting that there's information, something has happened to cause a solar eclipse when we wake up one day. So this, that we don't see the sun in the morning. Another way to think about this is if we observe a never before seen mutation in someone's DNA in a highly conserved region of a transmembrane protein that causes a new type of disease, we have learned a lot from this rare event. So diseases, they are caused by very rare mutations. There's millions of mutations that we have different from our parents' DNA, and most of them don't do anything at all in terms of disease. But if we discover a new mutation or a new mutation that causes some disease, this is big news because you alert the press, you write your paper up. We found a new mutation that causes epilepsy or something like that. So yeah, rare events, they carry more information than non-rare events. And this is a nice way to think about it. Let's calculate the total information in the system using the Shannon entropy. So we've done that worked equation here. So the Shannon entropy H is given by the sum of minus P log P. And we have two two class representations to factor in. So we do minus P log 2 for the blue balls plus minus P log 2 of the red balls. And we end up with 0.81 bits of information. So this is less, even though we have the same number of outcomes, because of the class imbalance, we have less information in this state than in our equal probability state where we have 3 bits. So why is this? This seems a bit strange. I was just telling you that even though non-rare events don't carry much information themselves, rare events do carry a lot of information. So why are we not seeing more information in this state than in an equal probability state? So yeah, I've kind of come up with another analogy to maybe make this a bit easier to understand. So imagine you have a really boring job where items arrive on a conveyor belt and you must sort those items into their corresponding boxes, and you get paid commission for each item correctly placed in its corresponding box. Well, in an equal probability system, each item correctly placed will pay you the same amount of commission as any other item. So this means you need to be paying attention at all times, because where there's 4 different items, every time you mess up one item, you're losing 25% of your commission. So you need to be paying attention at all times, because every item carries the same level of information or the same amount of commission, if you like, if you want to think about it like that. However, if we have a state where 99% of the time the conveyor belt gives you one item or item A, and 1% of the time it gives you item B, you could say, well, if I just put all the items, regardless of what comes out, in box A, I get paid 99% of the time. And so you just don't have to pay as much attention. Whereas in the state where the equal probability is crucial, you lose commission if you just you lose a quarter of your commission every time you get one box wrong, if it's in a 4-state system. So I hope that kind of helps you think about how an equal probability state carries more information on average, because you have to pay attention to every single different state in the system. But 99% of the time, we have a rare event. Obviously, you'll miss out when you experience a rare event, but you get less information because you have to, think of it as you have to spend less time or less attention on this conveyor belt. And this can be contextualized with something called the binary entropy function. So we have our Shannon entropy on the left, and we're plotting against probability. And what the binary entropy function says, that you maximize the information in a system where you have equal probability. So, this goes back to our example we were just given. Obviously here we only have 2 states, 0 and 1. Sorry, 0 and 1. This is a binary bit, if you like. And we have, we maximize the information in the system. We have equal probability. So how can we apply what we've just learned about measuring information in equal and unequal states to decision trees? So if we think about our data before, when we have our training data, we need to ask a question to split these red and green apart. So we can measure H before. So we can measure the Shannon entropy in any of these 3 boxes on their own. So that's what we do. So we measure H before, we ask a question, and then we say that H after is H left plus H right. So H left plus H right. And the information gain, and remember, this state carries the most information at the start, is equal probability. When you start asking questions and splitting the data up, these individual boxes, or the child nodes, they don't carry as much information as their parent nodes. So what you can say is that the information gain is the H before, Shannon entropy before, minus the Shannon entropy after. And depending on how you split the data, you can see that the information gain will be smaller or larger based on what happens with H after. So bad question. If we have our equal state before in the parent node at the top, and a question will just take one of these data points and put them on the left, but the rest stay on the right. Well, clearly we know intuitively this is a bad question, because although we've learned a lot about this one data point, we've not learned anything about the remaining 99.99% of the data set. So, we've ended up with high imbalance after the question, which is not good. Remember, balanced states, think of the binary entropy function, balanced states contain more information. So this is a bad question, and you can see why that is. A good question might be this. So we've split actually most of the green data points onto the right-hand side. We've still got some over here, but you can see that we've split the data in a certain way. And if you plug in H before minus H after, you will see the information gain is larger in this case than it was in this case. So again, this is a bad question. Even though the column that you've used might be a good example, this might be an example of using a bad threshold or something like that. But the point is that you can measure the gain in information based off a split of data. And this is what we were talking about before. We're trying to teach these algorithms to learn which questions are good to ask of your data for a classification problem. And Shannon's theory, or the Shannon entropy, gives these algorithms all the tools they need to assess if their questions they're asking are good or bad. And so decision trees, that's what they'll do. They will just take the data, the original training data, and when it comes to deciding the first question, it wants to decide the best question, because remember, you want to ask about blood pressure for everyone, but you might not want to ask about how much exercise you do if you're really old. That might be a pointless question. So it wants to ask all the big hitters first, and it will just iterate through all of the features and various different thresholds for each. So it goes through 1,000 different questions and how to ask those different questions, and it just reads off the maximum information gain. So out of the 1,000 different questions it asks, the last one maybe gives you the most information, and it will go with that as its first question. So this is called a greedy algorithm. So if the guys in comp sci CDT, I'm sure you would have come across greedy algorithms. But yeah, decision trees, they pick their questions in a greedy way. They will pick the big questions first, and they'll keep going down until you have less relevant questions. So are you not splitting the data as well? And remember, just think of whenever you think of decision trees or algorithms asking questions of data, just think about entropy, or the Shannon entropy. It's trying to maximize the difference in entropy before a split and after the split. So it keeps doing this until the leaf nodes start to become unbalanced. After a certain number of questions, the potency of your questions just won't be as good. And it's at this point that you say, right, well, what are our leaf nodes? We want to get to an unbalanced state towards the end, because we know that if you have lots of people that had a stroke in one leaf node compared to maybe a minority which don't, then you know that someone else being asked those questions and ending up in that leaf node, they will have a high chance of stroke. So this is ideal for classification purposes. So let's talk about training and testing, just to reconceptualize how decision trees work, and then we'll talk about random forest. So we would split our training data away from our test data, as we did with logistic regression. We use the training data to build the tree structure, what questions are being asked, optimize those questions during the training process. So we might end up with something like this. Based on our training data, this is our boundaries, and they're pretty good. I think some partitions. This one isn't so great because we've still got a 50-50 split. We do that in training, so we optimize which questions we're going to use. And then in testing, we would just send a sample down the tree, just falls all the way down, whichever leaf node it ends up, then you can read off the class probability and therefore the class. So that's decision trees. A lot of the theory that we've talked about is applicable to random forests anyway, especially how you measure information. It's exactly the same. But yeah, decision trees, the fact that they're greedy, they tend to ask really big questions. And we know that in rare cases, asking just the big questions is not enough to tease out the best way to classify rare classes. It might just be that a really strange random question, or you ask a series of random questions, and suddenly you actually see, oh, I've managed to split the rare class away from the rest, just by using really obscure questions. And so Leo Breiman introduced random forest to in part address this issue. This is a fairly new technique, random forest, compared to things like neural networks they were invented in the 50s, maybe even 40s. Bayesian probability, 1758, and so on. So this is quite a new technique in terms of machine learning. We're trying to address this issue that greedy algorithms don't necessarily work for every situation. And so instead of optimizing questions in the way that you would go through every single column of data and use multiple different thresholds for every column, we're going to do something slightly different in random forest. So instead of just having one tree where it's absolutely crucial that with each question, you split the data in the best possible way, how you gain the most information, we're not going to worry about that so much, because we're going to split the problem up into lots of small problems by introducing many trees. So we'll have, there's often hundreds, even thousands of trees. And what you're going to do is down each tree, so we still have our training and test data. So right at the start, before we even split up into trees, we take our training data and we just keep our test data aside for a moment. That training data, again, will randomly sample 75% of that training data and send it down one tree. Down another tree, we'll send another random sample of data. And we keep doing that across many hundreds of trees. That means that when we do that sampling, each time we have an out of bag, or it's called bagging. So remember, this is all on our training data, but our test data, just keep that out of mind. It's not doing anything. When test data is remained separate. So even down each tree on our training data alone, we still take a subsample to send down the tree, and we hold back some data as an out of bag, which you can do internal testing on. I'll talk a bit more about this when we look at cross-fault validation on Wednesday morning, I think it is, or Thursday morning. Yeah, so we send random samples of data down each tree, and we ensure that they're different. And instead, at each node, where we go through all the features and optimize to find the best feature, we just choose a random number of features. And I think the default in random forest is at each decision boundary, you choose the square root of the total number of features. And you only optimize on those random features. So when we look at the notebook, this is a parameter called mtry in R. And so if we had 49 features, we wouldn't go through all of them and find the best one. We would choose 7 random features and only optimize on those features. So what's the result of doing this? This seems a little bit strange, because I was just trying to sell you the idea that you can find the best optimal split on our data using decision trees. But of course, that's only when we have one tree. In this case, we have lots of trees, and each tree is going to learn something different from all of the other trees. And what each tree learns on its own is a very small amount compared to a fully trained decision tree. But the idea is that you split the problem across multiple trees, and then you aggregate the findings afterwards. But you have to ensure that each tree learns something different from the next. So for example, if we were to, if these was a forest of 3 trees, but we fully optimized each tree in the way that we do with decision trees. This tree would learn nothing different from this tree. So it's pointless. What we want to do is get each tree to learn something different. You know, you give it the opportunity to ask some more obscure questions, which is better for, you know, classifying rare examples, and bring all that knowledge together and aggregate it. And so you can see how this works. If you ensure low randomness in the way you ask questions, i.e. you're effectively optimizing on all questions, all the trees are highly correlated, but in high randomness, each tree structure looks different. And so you expect them to learn something different from each other. So remember, instead of training just one tree, we are training a forest. And so say we have 100 trees, because we have a different sample of data going down each tree, and we also have different questions, random questions, if you like, from each node, we ensure a lot of randomization in what each tree is going to learn. So any given data point will go down X% of these trees, and in each tree, a decision is given. So this is a bit of a strange concept. So in logistic regression and in naive Bayes, we had our training data and our test data, and we train on certain data points, and never is any of those data points used in the test set because we're biased in the test set. Remember, we only report accuracy on the test sample because those test samples were not used in the training process. So here, again, we've already done our test and training split. Our test data is way off. We don't even think about that. We'll bring that back in right at the end. But just for training samples, training purposes, what we'll find is that during training, any one given data point will be used in multiple different trees, but also that same data point will also be used in multiple different test out of bag samples. Remember, this concept of bagging as well. So, you know, random forest has its own way of doing training and testing, if you like. Now, if we have the same data point was used as a out of bag to test all the structured trees, there'll be a different decision each time. And we're just going to bring those together. So if one data point is sent down 3 trees and classed as label 1 in 2 of those trees, and in label 2, and was classed as label 2 in the 3rd tree, we know that it has accrued 2/3 probability of belonging to label 1. So, you know, that's how we can aggregate our findings across all of these randomly optimized trees. This is called a majority vote. So you'll often hear about this in random forest. The class probability and the class label is arrived at by a majority vote in this way. So this overall strategy is called divide and conquer. So, you know, we're splitting up our problem into lots of small problems, and you bring them all together to conquer the problem as a whole. And so this is different to greedy algorithms. Remember, greedy algorithms, they just try to find the best splits in order. In the divide and conquer technique, we don't really put priority on that. We're just going to say, as long as each tree learns something different from the other, when I bring the results together, I should arrive at the big picture. And because the divide and conquer or random forest technique doesn't put so much emphasis on finding the big questions, you'll end up asking lots of questions, and a fair few of those questions, they might end up splitting the rare samples away from the majority class. So, you know, random forest, you can see, might be better at addressing machine learning problems where you have a major class imbalance. So let's talk about black box. So Marcos, I'm sure, will talk about black box methods when he talks about neural networks. So far, when we looked at linear regression, logistic regression, and even naive Bayes, those 3 algorithms, they were all just based off one equation, you know, y equals mx plus c, or, you know, log odds equals y mx plus c. And so those are easy to understand because it's just one equation. What we've talked about here is an ensemble technique. So, you know, we do things like we construct our tree using Shannon entropies. We will randomize things if we're doing random forest. We will take majority votes. in the case of, hundreds of trees. So there's lots of little steps in how you build up decision trees in random forest. There's not just one equation. And I think unfairly, decision trees, random forest, neural networks, they get called black box methods or techniques. And basically what people are saying is that we don't understand what's going on in this black box. You put data in, you get a result out, and I'm not going to trust that method because I don't know what goes on in the middle. And this often gets thrown at a lot of machine learning techniques. Decision trees and random forests are no different. And unfairly, they tend not to be trusted because of this. And people say that they lack interpretability, like they don't know why it's arrived at the decision that it has, because we can't see where's the equation, where's the regression equation that we're looking at. And but what we've shown in this lecture is, even though there are lots of little steps, each step in itself is simple. So just where logistic regression and naive Bayes was looking at probabilities, well, so does decision trees and random forest. When you're asking questions to split data, all you're doing is calculating the Shannon entropy, which is just logs and probabilities again. So each step is simple on its own, but there's lots of little steps put together, and that makes it maybe a little bit harder to understand. Now, I want to talk about something really important about decision trees and random forest, and this is a byproduct of the Shannon entropy. So, if you're asking questions of your data, and this applies in random forest or decision trees, every time you ask a question, you measure the information gain. So you know that when I asked about blood pressure, I gained more information overall than if I asked about how much exercise you do. So this means that we can rank our columns of data based on how important they are to our classification process. So we can say, for this is the iris data set, the famous iris data set which is in R or Python, and you're just trying to classify what species the plant is based on sepal width, length, and petal width, length, and so on. And decision trees and random forests, they have, because of this inbuilt notion of measuring information, they can tell you which features were important to you in the classification process. So decision tree, this is easy because what you find is that one feature tends to just be used once in a decision tree, unless you have large decision trees where it might be used again. So when you have your first question, you go through all the different features to try and split the data, and you find just the right threshold with just the right feature, and you say, I've actually found this much information when I ask this question. In random forest, because you have lots of random trees, and each question is randomized based on this m-try parameter, the same question gets used lots of times. The same feature gets used lots of times across these hundreds of trees. And you just simply take note, every time that one question was used, how much information was gained. And you sum up the amount of information that was gained every time that particular question was asked or that particular feature was used. So again, even in random forest, you can sum up the information gained when you use certain features. And what you'll find in random forest, the random forest package or the decision tree packages, is that there are kind of two measures that get reported to you. This is on the left, the mean decrease in accuracy. This actually doesn't have anything to do with information gain. You can do this method for any machine learning technique. Basically, what you're saying is, I'm going to leave one feature out and see what the accuracy was when I left that feature out. So, if you were to leave out petal width, you would say, I have a 7% or 8% decrease in accuracy overall. So you kind of measure how good a feature is by how much it contributes to classification accuracy. Now, on the right-hand side, you'll also get this in the output in the random forest package, is the mean decrease in Gini. So think of decrease in Gini as information gained or entropy. These three terms, Gini, information gain, entropy, Gini impurity, they get used interchangeably. Gini impurity, it just happens to be adopted more in economics, but they're the same thing. So this would say, for petal width, every time a question regarding petal width was asked, I sum up all those little bits of information gained, and it equaled this much information gain in total. This is the entropy in total. So it's a bit of a confusing way. Decrease in Gini, just think of it as information gained. So this means that, contrary to people that label these things as black boxes, you have a lot of interpretability from decision trees and random forests, even from neural networks, which I'll admit is more difficult to get your head around. But the same thing applies. What you'll find in neural networks is that you're actually using lots of things like logistic regressions in combination with each other, different versions of functions like that. So if anyone says that these machine learning techniques are just black boxes, don't trust them, you can say no. So before we go to the notebook, in summary, decision trees and random forests are ensemble classifiers. They use multiple algorithms piped together to achieve their goal. Decision trees try to optimize splits using a greedy process. And decisions are created with class probabilities calculated at the leaf nodes. Random forest grows multiple trees where each tree randomly chooses bag data and random questions. Decisions are made by majority vote across all trees, i.e. this is a divide and conquer approach. So think of the Ents in Lord of the Rings coming to their decision. Both methods use information gain, Gini index, to track feature importance. And so we'll look at feature importance in this notebook coming up now. And we're going to look at some natural language processing. So we've used pretty basic database style data so far. Let's look at natural language processing in this notebook. So on the Kaggle PM402 page, if you just click on the decision trees and random forest notebook link, this one here. Yeah, so the last three notebooks we looked at, we were actually able to do the machine learning phase in just one line of code each time, because R quite handily and Python as well. A lot of these libraries, they're pre-built, they're optimized to make the scripting as painless as possible. So I think what we are going to look at in this session is a bit of what would probably be classed as feature engineering or data engineering. And instead of using just easily well put together in advanced database style data, we're going to look at how we can use unstructured text in machine learning techniques. And I will say that the data that we're going to use today could well have been used in logistic regression or the naive Bayes algorithms as well. So, decision trees and random forest, they're definitely not uniquely qualified to look at NLP data. We just happen to look at some NLP data today. So our setup is pretty normal. These are the two libraries, random forest, as you can tell, and R part is the decision tree library. The data that we're going to use today is from the movie review package, from the text to vec package. So I will talk about vectors shortly and how this relates to this problem. But this text to vec package is going to do a lot of the NLP processing for us, and it comes with a nice toy data set called movie review. And it looks like this. So we attach the data to our session. And then the first example is this. So we have three columns. We have a document ID. We have sentiment. I'll talk about this in a minute. We have the raw text. This is just a movie review, and you can read through all of these. And the sentiment column is there to say whether it was a good or a bad film, where I'm going to presume that one is a bad film. So this is the data that we're working with, and you might be thinking, well, where are the columns of data? Where are the features that I put into my formula? Typically you had something like this. I don't know. This kind of formulaic approach. Oh, where's the tilde gone? I've got an American keyboard, but anyway, you know what the idea is. You put your label column against all the other columns in your algorithm. How does this work in here? So that's the what we need to work through today to figure that out. First, though, let's just explore our data a bit more. And crucially, get some training data. So the first 300 reviews, if you like, are reserved for our training data. And as always, we want our target label to be a factor. As you can see here, when we took the summary of our movie review sentiment column, it's not a factor, it's an integer. So we're just going to turn it into a factor. Okay, so how do we start even processing this type of data? Because, you know, what we'll see in this notebook is that 90% of the work is in processing this data, and the machine learning step comes right at the end. So in this text-to-vec package, we have a lot of functions that can help us in processing this unstructured text. And the first thing that you tend to do with large volumes of text like this is to tokenize your data. So we would like to get to the stage, actually, where all of these words are its own column in a data set. So think about, you know, you have blood pressure, cholesterol, things like this as columns of data. What we would like to do is to spread all of these words so that each word is its own column of data, and the values of those columns, you're just counting how many times the word occurs in a document. So a first step to do it is to tokenize our data. And there is a nice function called iToken. And what this is going to allow us to do is to start splitting all of our words across a set of columns. So there are a few parameters that we want to put in. So, you know, by the way, whenever you're using any function, I always encourage you to just look at the documentation. So just put a question mark, iToken. Where's it gone? Oh, sorry, double question mark. It's telling me down the bottom. Have I run the library? Ah, here we go. Needed to run the library first. So yeah, you can see, you know, all sorts of things you can put in. Just as a bare minimum, I'll describe the parameters I'm putting in. So I'm putting in the raw text. So this is this part. I'm doing a few things. I'm converting it all to lowercase. This can help with things, you know, you have lots of acronyms and so on. If you don't want to use case sensitivity, you can just leave this blank if you wanted to. And I'm going to do this by word. So you can tokenize documents in different ways. I could tokenize this at the sentence level. So I could have rows of data where each row is a sentence of data. But I'm going to tokenize this by word. So split it up word by word. The output doesn't really give you much. It's just giving you that is an object of some form. It doesn't really matter. What we want to do next is get an idea of all the different words and how often they occur across all of our 300 reviews. So the way to do this is to use a function called create vocabulary. And remember, we've tokenized our reviews and stored it in an object called it, or iToken, and we wrap it in this create vocabulary function called vocab. And here you can see, this looks a bit strange because there are numbers in the text as well, but as you carry on going down, you can see that the word at appeared 285 times across the 300 documents, and it appeared in 143 documents. You can see the headings there. So this is good. We're already getting a feel for how often certain words appear. Now remember, back to our Shannon Entropy, rare events contain more information. So words like the, at, you know, he, she, and stuff like that, they don't contain as much information as words like terrible, or I don't know, amazing, things like this. So, you know, this goes back to when they were trying to break the Enigma code, you know, certain words carry more entropy. So you pay attention to those sorts of words. So we know already that we have terms, unfortunately it's truncated it, but we have certain terms which are more important. So, a date, for example, that can tell you a lot about maybe the type of film that you're looking at. But the word at doesn't tell you anything really about the type of film you're looking at. So, we can already see, just using an argument of Shannon entropy, which features would be more likely to help us out in a classification problem. And for that reason, what we can do is we can remove these low entropy words or low information words. So there's a few different ways to do this. You can just manually create a list of stop words, and you can put those in, and in your create vocabulary function, you can just declare that stop words equals this, and we're just removing these words from our vocabulary. So that's one way of doing it. Another way of doing it, it's quite a flexible way, is this prune vocabulary function from the text-to-vec package. So after you've created your vocabulary, vocab, there are various different options or parameters you can input to trim your terms. So for example, I'm using this one called term count max. So this will filter out based on the maximum number of occurrences over all documents. I think this is the easiest to understand. You can do this based on proportion of documents. So we've got two columns, term count and document count. And I encourage you to explore all the different ways to reduce common words in your data set. And that's what you're trying to do. You're trying to reduce common words which have less information. So I've just said, get rid of terms which have a maximum, which have a count across all documents of over 100 or 100 or more. So this leaves me with, there you go, words which don't appear more than 100 times. And yeah, you can see, you can probably see some of these words, they might have more relevance. As you got like love, that's got a lot of information in it compared to the word there, for example. So, that's what we're trying to do. We're trying to get a nice set of features, feature selection, trying to select features which we think are going to be useful to us. And this is how we're going to take this vocabulary. So at the moment, they're in rows. And we need to get this into where we have each word is its own column. So we're going to spread this across columns instead, or we're going to transpose the table. And we're going to use as values the number of times a word appears in a certain document. So there are probably a few different ways to do this. I'm going to use the way that's using functions from the text-to-vec package. And this is, by the way, this is a dplyr chain. So to make this a bit easier, remember dplyr does things like this. So if you have, a of x, if you want to pipe that into another function, dplyr, you can just do this. B of x. But this would actually mean in base R, you'd be doing something like this. So if you had a of x, you'd have to wrap this in B and C and so on. So these dplyr chains, they just pipe in outputs of a function into the next function. So if you've ever done piping in Linux, is a similar thing. Okay, so when we talk about this transposed table, which I've already kind of showed you what it looks like, we're talking about something called a document term matrix. So we're taking this, easily understandable vocabulary object, we're going to spread it across, transpose it, and make sure that each word is its own column. Is often called a document term matrix. It's just a fancy name. So you take our prune vocabulary, which we saved here, which is this object we're looking at right now. Then there's a function called Vocab Vectorizer. So this will create the counts per word. And then this create DTM object is going to take this object in here. So by the way, you don't even need to do this. You can just do that. However, when you have two input parameters from the previous objects, you can declare them explicitly if you like. So it doesn't really matter. So we're going to take our Prune vocabulary, get the counts, and then spread it across all the columns, and we're going to convert it into a matrix. I wanted to go directly as a data frame, but it turns out that you need to convert to a matrix first to turn it into a data frame. But anyway, you end up with something like this. So this first row is the first movie review we have, and it's saying that the word most appeared 4 times. The word great didn't appear at all. So this is how you read this document term matrix. And I know it looks really crude what we've done. Maybe you're expecting something fancier to deal with NLP data, but we do need to get it back to, these algorithms written in our Python, they're designed to work on database style data. So we need to torture our data to make it look like a database, if you like. So this is what we've done. And now we can just put this into our random forest function. So we take our document term matrix, which is this object above, and we feed in our training, our ground truth labels. And we just save it as an object called rffit or rffit, random forest fit. So there's a few things. We can plot it, call the summary of it, and so on. So this is our summary. We've got our confusion matrix spit out at us, which is quite nice. And also you can plot this. So in the lecture, I mentioned something called out of bag or bagging in random forest. We are going to test this further down on an independent test set. However, in random forest, this particular implementation in this function, the random forest library, random forest does bagging for you and outputs in a plot. So what this means is that even though we've got our training data split apart from our test data, we're going to have 100 odd trees, or in this case, there were 500 trees. And random forest subsamples the training data again, so that some is used for training, and the out of bag, this black line, this is our internal test data, if you like. And so what we have is that the plot is really nice at visualizing the effect of the number of trees you use in random forest against the error. So one of these red or green lines is either the good review or the bad review. I would suspect, without looking, my hypothesis is that the language will become more colorful and more emotional around bad reviews, maybe. And so you might think that this red line is the error in determining bad reviews, and the green line is the error in determining good reviews. This out of bag, again, this is the independent sample, so it contains both good and bad. And you can really see actually that as you increase the number of trees, you reduce the error, but only to a certain point. It becomes pointless after maybe 100 trees to continue adding more trees. It just takes more time. So that's a nice feature of random forest. You get to visualize the error over the number of trees, and this is our feature importance. So this function comes from the R random forest package. You just put in your fit object and call var int plot, and it will plot different things. And you can clearly see that the words like great, worst, awful, poor, these are the most useful features in helping to determine between a good and a bad film. And you can clearly see how well this correlates. So, not only could we use random forest to classify between a good and a bad review, we could purely use the feature importance output of random forest, or we can just leave one feature out if you like. So you can use this on any machine learning algorithm. We can look at, well, what is the language that tends to get used between good and bad reviews, or if we were looking at a healthcare example, anxiety and depression, things like this. So it's really useful. So testing. So testing is a bit strange, because if you recall, when we do training and testing, the same columns in the test set need to also exist in the training set, and vice versa. Now, when you take an independent test sample from here, we've got lots of different features, or i.e. words, and it will almost always be the case that in the test data, there will be words in there which were not available during training. They weren't in the training data. So you have to think of two ways to handle this. I'll briefly discuss two of those. This is just a complete version, by the way, of training, all these cells put together. Now, when we get to testing, there are a few things that we can do. So let's break down. We've gone through all this code in the cells before. We trained our random forest, so on. Now testing, excuse me. Okay, yeah, so we've got our independent test set. So remember, we used the first 300 reviews in our training data. So we'll just use the next 100 for our test set. Now, what we can do, and what I've looked at in the behavior of the text-to-vec package, is that if we don't create our own vectorized version, so remember, if I just go here, yeah, here we go. We did our vocab vectorizer based on our Prune vocabulary using the training data. We can actually just use this same object vectorizer when we do our test data. So we can tokenize our data as normal. We always have to tokenize our data because it's a big block of text. However, when I do the create document term matrix, instead of creating this document term matrix based on counts purely on the test data, I can just feed in the vectorized version from our training data. Effectively, what this does, which isn't too desirable in my eyes, is it ignores new words from the test data. So if you get new words in your test data that you might think are important, they're not going to get included, or they're not really represented when you train the model. So in some ways that's bad, because it means that any new words that you get in your test data, it's not being taken into account in the decision. Another way you could do this is when we did the Prune, we built our vocabulary and our training data. You could build the vocabulary using the test data as well. So i.e. use the vocabulary across all of the reviews that you have. Now, some machine learning purists would say that you will introduce bias into your test data because you're using words in your test data that is going to be used in training, or at least because when you have a sparse matrix, you have this object. So even though the words that you see, you have a word in the test data which isn't in the training data, it does still get represented in some way in the document term matrix, because you say that across all the training documents, this certain word appeared 0 times, i.e., this could be a super rare word, so that when the test data comes in and then you finally see that word, it's like you really pay attention to it. So you're biasing the data in some way. So, neither way is perfect, because if you were just to ignore the words used exclusively from the test data, then you're not using that. But the other way is if you used it to create your vocabulary at the start, you're biasing your data in some way. So, it's no perfect way, and I'm sure other people have looked at certain ways to incorporate this, but I've just showed you a way to just ignore the words in the test set. As I said, I just feed in the vectorizer from the training data, and I spread my test data according to the words in the training data. And then, of course, you can just use our nice predict function as normal. And yes, you can get your confusion matrix. There you go. So I hope, this has given you a bit of insight into, feature engineering or data engineering. The random forest part was just 1 line of code again. And we had to put a lot of effort into squeezing our data into a certain way just to get it to fit into this random forest function. So as an exercise, you can use random forest maybe against decision trees. So, the app, all you have to do to use decision trees is just pretty much change this to R part and so on. So you can do that and maybe test that against naive Bayes and logistic regression as well. Okay, so, our next session will be on SVM and hyperparameter tuning tomorrow.